Okay, so in this video, we are going to be talking about how temperature and concentration change in a system with a constant flow going in and a constant flow going out, and we are saying that the system is perfectly mixed. So here, if we take a look, um, this is our system right here, this little box, and then it has a stir in it, and it we're going to say that the liquid inside the system is pure water, and the liquid coming into the system, um, at which we're going to represent as Q in, is coming in at 320 Kelvin, and then the initial temperature of the system is at 300 Kelvin. So we're going to see how that temperature in the first section. We're going to see how that temperature changes with time. The tank also has a flow rate going out represented by alpha times the square root of h. And then this tank has a cross-sectional area of A represented at the bottom and a height of h. And we're also going to see how the height changes with respect to time. So to start off, the first thing that we are going to want to do is we want to know the change in mass of the system. And since we don't have this in terms of mass, we can kind of manipulate the variables a little bit. So we can say our change in mass of the system is equal to the change in mass of the stuff going in. So the change in mass in, and then minus the change in mass going out. And from here, we can then take the mass, and since we know the density of water and everything like that, it's going to be density times the volume, and we can figure out the volume because we have our cross-sectional area and the initial height of the tank. So then we can go ahead and kind of manipulate those variables a little bit. So then if we say, so the change in mass is going to be the change in density times the area times the height with respect to time. And then this is going to, instead of placing it around, almost we're just going to say this is equal to the density times the flow rate going in minus the density times the flow rate going out. So Q out. And the reason we do this is because the units actually cancel out, and we can see that the density times the flow rate, since it's in cubic meters per second, the meters cubed, the cubic meters cancel out. So then we get just the kilograms from the density, and then we have the mass right there. But instead of writing it like this with Q out, actually, what we can do is we know that Q out is represented by alpha square root of h. So we can just substitute that in, have the eraser on, square root of h. And then what we can do from here, since we know that the cross-sectional area and the density are not changing with time, it's always going to be constant. So we can go ahead and pull both those out, but then the densities can cancel out right here. We can just pull the A out, so then it can end up just being the cross-sectional area. Cross-sectional area, so dH over dt is equal to the flow rate going in minus alpha square root of h. And then we can just divide that A over right here. So now we have the change in height with respect to time of the tank if we know the flow rate going in, which we do, and everything like that. Now, the main part of this problem is we want to know the temperature, and we can't really do anything with that from this. So what we're going to do is we're going to apply an energy balance, or an energy / mass balance almost. And if you recall, so the change in mass and the energy of the system would be equal to the enthalpy of the system and the kinetic energy and potential energy times the change in mass minus all that, everything like that. But what we can say is we know the kinetic energy and the potential energy of the entire system is we're going to go ahead and say it's almost negligible for the system. So we can just completely simplify that down and really what it's going to end up being. So the change in mass of the system times the enthalpy of the enthalpy of the entire system is going to be equal to the enthalpy going in times the mass, I believe, minus the enthalpy going out times the mass. So then what we can do from there is kind of the same thing, is we can apply what we did above and substitute it out for with the density times the volume, which is the area and the cross-sectional height and everything like that. I guess this would have to be the change in mass. So then the change in density and then plus the internal energy is equal to the enthalpy going in times Q in times the density, but the same thing. We'll figure this out later. But enthalpy going out and then the change in mass going out. So that alpha square root of h. So then I can go like that, but then again, the densities will cancel out once we divide it over, because we can pull it out because the densities, again, are not going to change with time. Neither is the cross-sectional area, so we can go ahead and pull that out. Oh, I just completely messed it up. So area times that, and this is still with respect to time. And then with the area pulled out, we can then further this out, but then we can also recall that the equation for enthalpy, or not enthalpy, the internal energy and I guess the enthalpy of the system, excuse me, the enthalpy and the internal energy of the system are represented by a specific heat and specific volume times the change in time. So that's like the change in those energies are with respect to temperature. So dH is equal to the specific heat, or the heat capacity, or specific heat capacity with the change in time, and then du is the specific volume with respect to temperature. Or no, those are wrong. It's the, and bueno, that's okay. Yeah, so wrote that wrong again. The change in internal energy is the specific heat capacity, and the internal energy is the specific volume. So now we have the change, we have dH and du, which we have in the equation above, and we can kind of substitute, those in pretty much, and kind of work the equation out from there. And also we are going to say, for this case, so the both CV and CP are going to be equal in this case. So yeah, after we say that CP and CV are equal to each other, so what we can do from here is, so the change in both of these, so let's say du, okay, so the change in the internal energy would be the internal energy at a certain point minus a starting internal energy, so it's almost like a reference point, so we can say that's u naught, and then this will be equal to the specific heat and then the change in temperature, so again, a temperature that we're measuring, I guess, minus an initial starting reference temperature that we had measured. So then what we can do is we can plug this back in, but instead of having all a more extended out, the reference temperature can be anything it needs to be. So it could be 0, it could be 200, whatever, but that initial reference temperature is not going to change with respect to time because we had set it at a initial temperature, essentially. So we can just completely get rid of that and just write that as in terms of T, and same thing with the initial reference internal energy. So it'll just end up coming out, but that doesn't matter because we're substituting it in anyways for the du because it's the change. So we can go ahead and keep that aspect of it. So what this will end up being is A times the change the change in height, and then CV times T with respect to time, so dt, and then this is equal to CP, and then same thing, temperature, and then we still have Q in, and then minus CP, the temperature, and then alpha radical height. So then, since we earlier said that CP and CV we're going to set those equal to each other for this case for simplicity, we can go ahead and pull that out with the A and just completely cancel those out. So then what this is going to be, well, we can factor it out and then cancel it out. So then it'll end up being A dHT over dt, and this A is out here, is equal to the temperature Q in minus the temperature alpha radical H. Now, to get the respective temperature, we can split those apart, and we can't just completely separate them. We have to do some calculus, but essentially it'll work out to be the height and then times dt over d little t plus the temperature dH over dt is equal to the same thing, T alpha radical H, and then we can't forget the A, but we're going to go ahead and put the A over on the other side now, and then since we want respect to temperature, we can just kind of subtract that part out from the other side. So it'll end up being H dt, or no, we can't do that. H times the change in temperature with respect to time is equal to all of this again, H over the area, and then minus the first thing, so the temperature times the change in height with respect to time, and then we can just get rid of the H, so we can divide that over. And all of this will be divided by H. So now this equation right here is our change in temperature with respect to time. And then the reason we found the change in height earlier too is so we can apply it in this equation at the end here, and also we want to figure out the change in height of the system over time, because the flow rate going out is smaller than the flow rate going in, so we want to kind of be able to monitor that and everything like that. Now, the second part of this is, instead of talking about having an initial temperature and everything like that, so let's just mark this off. If we were talking about the concentration, so let's say we had a certain negligible density of a compound within the water, which we'll be using as the solvent In this case, still just to keep the densities the same and everything like that. Then we want to figure out how does the concentration change over time as we're flowing it into the perfectly stirred kind of tank. And what we can actually see, so what we're going to say at first is, so the concentration of the flow rate out is going to be exactly the same as the concentration of the system, because we're saying it's perfectly mixed, and that'll play a big part in this. So if we kind of think back, so the change in mass, this is familiar because we saw this at the beginning. Now, instead of doing this with density, what we're actually going to do it is with the concentration times the area times the height, and it's just going to follow the exact same steps and the exact same everything that we just did. So if you imagine, so I'll change color here. So this density that's right there, if we just change that with the C, it's going to follow the exact same steps. So we're going to pull it out, we're going to get rid of it, and then all of our stuff is going to be the exact same here. The only difference is instead of using temperature at the very end with specific heat and everything like that, it just kind of, the concentration almost makes its way in there and it follows the exact same equation, and that's going to make it a lot simpler once we do run over to the code and everything like that. So yeah, so we'll jump over to the code. Okay, so now we are in the code part of this, and I just took the time so we didn't have to spend it. I imported numerical Python. I also imported the solve an initial value problem from SciPy, and then I also imported the subplot because we're going to want to make a plot of this, and then these are all of our initial values. So we have our area, our initial height, initial temperature, the temperature going in, our flow rate in, our alpha, and then for later on in the plots, the length and time of seconds that we are going to kind of monitor the kind of values for. So the first thing what we're going to want to do is we want to input the equations that we found in the previous section. So what we're going to want to do is define the for K, and then wrong side. And then from there we can kind of unpack. So our T and H is equal to our K, and then now we're going to put in our function. So our change in height is equal to, I have the formulas here. So it's equal to our Q in minus our alpha that I just put as lowercase a, so Q in alpha, and then that is times our H. So we actually can do another one. So our initial height squared, or not squared, it's square root, so 0.5, and then that's going to be all divided by our A. So then we need to do divided by the area, and then yeah, that is the equation for that one. And then our change in temperature, or I can keep that as lowercase t. So our change in temperature is equal to our temperature going in times Q in, and then minus alpha times the height. Where's that? Times our height squared. Nope, again, wrong mistake. To the 1/2, and then that's divided by A. Our area right there, divided by our area, and then we subtract our temperature times our dH, and then all of that should be divided by H. So divided by H, close parentheses. So this needs to go in parentheses with that, and then all of this needs to go into a parentheses. So that minus that times that divided by A. Just trying to make sure all my parentheses are correct here. And yeah, I believe that is all for those. So then from there, we want to return an array of our functions. So now I'll push shift enter on that. Okay. So then now we want to do solve an initial value problem of this. So now we have our function in terms of t and h. We can solve the initial value problem. So okay, yeah. So what we can do here now is, so our solution is going to be equal solve underscore IVP, and then we want to pass in our function and then our t-span. So we want to do it from our length of time. Yeah, it's just t1. And then our initial conditions. So now what we can do is we can find our solution. So we can pass this into the solve p, and then we can pass in our function and the length of time. So we want it to go from 0 to t, our length that we, for 100 seconds. So then from there, and then we want to pass in our initial values. So we want it from h0 and t0. And then we want a method equal to, we are going to be using the Redel, and then we can also, we want our dense underscore output, we want that to be equal to true. You have to put it out. Equals true. Do I have that right? Yes. So then from there, okay, yeah. And then if we just ran this, it would give us a whole initial kind of set of equations, but we just want the solution from it. So we can do dot solution, and then we want for our plots, we can just do, or I think it's, it's numpy dot space, and then what we can do from there. So the start, we want it to start at 0. We want it to start at, or we want it to stop at t1, and then we can just pass in a number of points. So we can say we want 500 points if we want that. And then also we want to set our h and t to be equal to the solution of our, oh shoot, forgot to we can just say this is plot is equal to that, and then our plot So now we run that. Name T is not defined. Where did I put T? Right there. That should, our temperature, that should be T. It should be T. That's what it was. So T right there, make sure that nothing else is there. Okay. So I can run that, and then I can run that again. Okay. So now we can go ahead and plot this. So we can just say our figure is equal to make subplots, and then we want, so we want rows is equal to 1. No. Row column. Okay, yeah. Oh, we want 2 plots. We want 2 rows with 1 column, and then it goes. Okay, no, we want 2 columns. That's what it is. I was mixing up rows and columns. Okay. So now, figure dot add underscore scatter, and then we want. How come it is not? Hold on. Let me shift enter that. Okay. Now figure dot add underscore scatter. We want it to be in row. No. Okay, so add scatter, and then our x is equal to our plot, our y in this one. So we're going to do height first, and then we want it to be in row 1, column 1, and then figure dot add scatter, same thing, x equals plot, and then y, this one will be our temperature, T, temperature, and then we want it to be in row 1, column 2. If I did not make a mistake, this should give us not a straight point. Maybe I have this wrong. Okay, I figured out the problem. I was missing a negative and some parentheses. It was doing the completely wrong stuff. But now, if we look at the scatter plot now, this is our change in height over time, and this is the change in temperature over time of the perfectly mixed system. So we can see that it starts at the system starts at an initial temperature of 300 K, and it'll eventually get up to 320 pretty quickly, and then the height will constantly change until it gets to about a certain point. And that just has to do with the change in height and pressure, everything like that. So yeah, so now, like we said, with the change in concentration, so instead of this being a certain value, this initial temperature, it can be an initial concentration. So now every time that we have the initial temperature, we can essentially just change that to a concentration. So if we just change the concentration going in and everything like that. So if we go here, so we can change this. So a concentration and temperature, that's Cn, that's C, and then DC, and then the same. This is DC, time length, concentration. Okay, so now if we do all this, we can see now that the initial concentration, of course, we can change the starting value. Oh, never mind. You can see 0 is not defined. It's defined. Oh, I never changed everything up here. Okay, so now we have, what is the same different plots? What I was going to do is we can change, so we can say the initial concentration is something like, okay, we have 1 molar of whatever in there. And then, oh, that should still be 1. And then the concentration going in, we can say is 4 molar. So now, if we do that, we can say it's still on a 320 scale, which is very odd. Well, nevertheless, I find that very odd. It should not still be on that high of a scale. It should not cap out at 320. Something. Maybe I did it too fast. Nope. Okay. Well, nevertheless, the graph should look the exact same because it's in the same terms where it's changing some of the initial values and everything like that. But that is the change in temperature and concentration with time. Thank you.